This video is about molarity and dilutions. Molarity is a way to express concentration quantitatively, so we will have numbers that go along with this. And the equation for molarity, well, molarity itself gets a capital M abbreviation, and it equals moles, which gets the abbreviation N, divided by volume, which has to be in liters. So it'll help in these problems a lot if you think about the units. Molarity is moles per liter. When you look at the first problem, it says, what is the molarity of a 650 milliliter? Well, right there, if you think about it in terms of units, that's telling you we're going to have to do a conversion there because that has to be liters. So a 650 milliliter solution that contains 63.0 grams of sodium chloride. The other thing is we need moles, and we're given grams there. So the first thing I'm going to do is convert 63.0 grams of sodium chloride to moles. And to do that, I'm going to need the formula. Sodium has a very low electronegativity, so it tends to form cations. It's practically giving away its electron, valence shell electron. Chlorine has a very high electronegativity, so that gains electrons. So you end up with sodium that's a positive 1 and chlorine that's a negative 1. So 63.0 grams of NaCl. We want to convert that to moles. So since you start off with grams, you need grams on the bottom. 1 mole goes up top. The grams you get from the periodic table, and for sodium chloride, it is 58.5. You do the math for this, rounding off to 3 significant digits, because this number has 3 significant digits, and you get 1.08 moles NaCl. Now if we plug that back into the equation for molarity, because molarity is moles per liter, so we now have 1.08 moles. The volume was given to us in milliliters, but we convert that to liters. Just move the decimal point 3 places to the left. You get 0.650 liters. We divide this, and the answer is 1.66 molar is how it's said. You just write it as a capital M, and it's NaCl. All right, think about what the units are. It helps you get the problem started and what you have to do first. All right, we're going to move down. All right, number 2. How many grams of calcium hydroxide are needed to produce 500 milliliters of a 1.66 molar solution? All right, so we're working with calcium hydroxide. It's asking grams. We know we're going to need the formula for this. So calcium has a positive 2 oxidation number. Hydroxide is a polyatomic ion. It's OH with a negative 1. So when you crisscross all of that stuff, you get Ca, OH in parentheses with a 2 outside. And again, think about what the equation is for molarity, or what the units are. It has to be in moles per liter. Well, I give you the molarity, I give you the volume, although it's in the wrong units, but that's easy to fix, and I'm asking for grams. Grams doesn't come up anywhere in this equation, but what we can do is solve for moles, and then do a conversion to get the grams. So if I just write it as M equals N over V, we can rearrange it for N. N equals the molarity times the volume. So when we write this out, the molarity is 1.66 molar. Now what I'm going to do is I'm going to write the units out as moles per liter. Because this capital M, sometimes if it helps you, if you can think about it, is instead of capital M, think about it as moles per liter, and you're going to see why this works out. The volume is 500 milliliters, which are going to convert to 0.500 liters. All right, we did mass times volume, so the liters will cancel out, and what we'll be left with is moles. What you get is 0.830 moles of calcium hydroxide. And what we have to do is convert that into grams. All right, so we need the molar mass for that. Since you start off with mole, you put mole on the bottom. The number 1 always goes with that when you're doing this conversion factor. And the molar mass for calcium hydroxide is 74.1 grams for every 1 mole. So when you multiply 0.830 times 74.1, rounding it off to the correct number of significant digits, you get 61.5 grams of calcium hydroxide. That's how many grams you would need to get that molarity and that volume. Again, think about what the units are to figure out if you have to do conversions or not. All right, number 3 is now asking us for volume. And just like we have to know, we're going to need to know what iron 2 chloride is in terms of the formula. So what volume of a 0.88 molar solution can be made using 130 grams of iron 2 chloride? Well, the Roman numeral 2 is telling you it's iron that's a positive 2 charge. Chloride has a negative 1 charge, so you get FeCl2. And again, if we think about this overall equation, you have moles per liter. Well, now I'm asking you for volume. So if I start off with M equals N over V, when I solve for volume, when I rearrange it, what I get is N divided by M. Basically, the molarity and the volume switch places. So we can start figuring this stuff out. Now, I don't know the moles yet. I know what the grams are, so I have to convert this 130 grams of FeCl2 into moles. The molar mass of iron 2 chloride is 126.8 grams of FeCl2 for every 1 mole of FeCl2. The grams will cancel out. What we'll be left with is moles, and that gives us 1.03 moles of FeCl2. And that's what we're going to plug in over here for N. 1.03 moles. The molarity is 0.88. I'm going to write it as moles per liter, because now what you see, the moles are going to cancel out, and the units you'll be left with are liters. When you do the math for this, rounding it off to the right number of significant digits, you get 1.2 liters. A common mistake with a problem like this is actually just getting it rearranged for volume. That's a mistake that I see students make sometimes when they're going a little too fast. And again, think about what the units are to figure out how much work you have to do. Now I'm going to jump down to this one. Describe how you would make a 50.0 milliliter solution of sodium thiosulfate pentahydrate that is 1.50 molar. Now, a lot of times, people would see this compound and they just would get completely confused and not even know where to start. Take it apart. Since sodium is in there, sodium tends to form ionic bonds because it has such a low electronegativity. It's basically, like I said before, giving its electron away, its valence electron. Thiosulfate is a polyatomic ion. It is S2O3. It is on our polyatomic ion sheet. It has a negative 2 charge. Hydrate is H2O. Penta means 5. So when you put all this together, what you get is Na2 S2O3.5H2O. So when it says describe, we're going to have to write a little sentence there with that, but that's not going to be too big of a deal. So describe how you would make 50.0 milliliters of a sodium thiosulfate pentahydrate that is 1.50 molar. Well, if we think about our overall equation, it gives us the M, the molarity, and it gives us the volume, although we have to change it to liters. The one thing it does not give us is N. So that's what we're going to solve for. N equals molarity times volume. So what you get is 1.50, and again, I'm going to write molarity as moles per liter, times 50.0 milliliters, converted into liters, becomes 0.0500 liters. Again, you just move the decimal point 3 places to the left. The liters will cancel out. What you'll be left with is moles, and that's 0.750 moles of Na2S2O3.5H2O. Now, when we go to a balance, we never actually measure out moles. We have to get the mass of it, so now I have to convert that mole, those moles, to mass. I said that wrong. It should be 0.0750. So 0.0750 moles Na2S2O3.5H2O. 1 mole goes on the bottom, so I don't run out of room. I'm not going to rewrite the compound just because it's pretty long. But the molar mass of that, and remember, you include the pentahydrate in the molar mass. It becomes 248.2 grams. When you do the math for this, round it off to the right number, significant digits, it's saying you need 18.6 grams of that sodium thiosulfate pentahydrate. So now the description part. What I would do to make this nice and easy is I would say add 18.6 grams of Na2S2O3.5H2O, the sodium thiosulfate pentahydrate, to a 50.0 milliliter volumetric flask. And add water up to the line. The volumetric flasks have lines on them that designate where exactly that volume would be. So a 50 milliliter volumetric flask has a line exactly where 50 milliliters would be. So you want to put the solid in first, and then add the water up to the line. What you don't want to do is add the water up to the line and then add in the solid, because then that solid is going to cause the volume to rise above the line, and you won't have exactly 50.0 milliliters, which means you will not have exactly 1.50 molar. So add the solid first, then add the water up to the line, and you have that exact solution.